Hello everyone, this is Ivan and this is time for MATLAB and a coding a little bit, and today we will try to experimentally improve a probability-based approach for data fusion. As you remember, in aviation, airplane coordinates play an important role because it is a surveillance data which is used in different systems like traffic collision and avoidance system, like terrain awareness and warning system, and many others. And of course for autopilot system and all stability-based systems. That's why today we will try to uh, play a little bit with real airplane trajectories, and we will use the data of particular flight for data processing with different radars, and then we fuse results of our simulation obtained from different radars to get like fused data. Okay, first of all, let me just a second. Okay. First of all, let me mark you a few formulas for data fusions. In our previous video, we discussed maximum likelihood method, which fuse the data with a maximum posterior probability, which means minimize errors. That's why result of fusion will be represented in the two formulas, one for fused data and one for dispersion of this fused value. And in this case, opposite value for dispersion of each measured parameter, it is like weight coefficient. That's why we use weight coefficient here, and we need to divide by sum of these weight coefficients. And finally, dispersion, it is result of some opposite summarization of all weighted coefficients by each measured sensor. That's why two of these formulas give us fusion with the minimum error. And also, uh, quite important, I will be glad if you remember it, if we consider two coordinates, which is so common in navigation equipment, because altitude in aircraft, it is something different, and usually we've got special sensors for altitude measuring. That's why fusion of three different sensor measurements by maximum likelihood method give us um, a crossing area of all confidence ellipses of each measurement. That's why this result ellipses uh, show us that we minimize errors because final ellipse will be less than all of these ellipses. However, in reality, it depends on geometry of mutual location, because if this ellipse will be somewhere here, it means that this crossing area will be less, and it means that finally our result of fusion will be much more less. That's why in most cases it depends on geometry of error distribution. Okay. Next, I would like to switch to MATLAB, and we will try to work a little bit with example, in particular airplane trajectory. Give me a second. Yep. And here you will see that this example I don't want to quote because I will left it for you. I just try to describe already prepared code, which you also can retype or just download it from my website. That's why this code is done in form of live script in MATLAB. It is another option of coding, which is also very suitable for problems where we've got some description, then some calculation, and then some description. And in this case, we can mix textual data, pictures with codes and results of coding. That's why live script and live script editor looks a little bit different from usual script editor in MATLAB. And here we can decide code area or text area. That's why we just decide what type of line it should be, and just type like description. Then you will see highlighted part of code like clear vars, close all, everything is here. And also you can decide a type how graphs will be represented. We can decide between separate graphs putting at the right side of our screen, or we just can put it together in script. In this case, our script will be a little bit longer. Just a second. I will try to make it a little bit more wider. Yep. And then we will continue. Okay. Let me left it in the following form. I think you will see what I have. Okay, first of all, we prepare MATLAB environment for our computation. Then I download matrices with airplane trajectory. Here I've got three variables: latitude, longitude, altitude, and altitude here I've marked as h, like height of airplane flight. Then also I've got velocity, however we do not need it, and time of measurements. However, in our simulation we do not need it. In my previous videos you can find how you can easily grab this data from different ADSB hubs and then use real flight trajectory data for investigation of some aviation problems. First of all, let's plot an airplane trajectory. To do that, I just used a new figure. Then I will need to specify a size of frame, which I will represent for airplane trajectory. In Gaussian, that's like lat lim, minimum of latitude, maximum of latitude, minimum longitude, and maximum longitude. Then I will use a map function, which is part of mapping toolbox in MATLAB, which help us to get a particular projection for latitude and longitude data. Because using plot for latitude and longitude is not proficient because uh, because um, because usually in navigation we use specific projections for data visualization, and we cannot use Cartesian reference frame to plot spherical coordinates. It's not a good idea. Then I will use function GeoShow to plot latitude and longitude in degrees, and also I will mark identification of departure and arrival airports. It is Cairo Airport and Bristol Airport. And here at the end of my figure, we can see what we've got. We've got uh, a GeoShow picture with latitude and longitude, and we've got our trajectory. Okay, next. In order to play a little bit with weather data, um, we will try to evaluate surveillance data. Thus, first of all, we need to select three different weathers, and in our example, I will use AIP of Ukraine and then just grab three enrolled weathers, which has area of operation up to 600 kilometers. That's why I just grab Kharkiv, Boryspil, and Odessa weathers. Thus, I put titles at specific variable, string variable, and location of these weathers, latitude and longitude, in particular matrices. Then I will transform coordinates of airplane trajectory to the coordinates of each radar. That's why, first of all, I will transform airplane location trajectory, which we got latitude, longitude, and altitude in VGS84, to the ECF reference frame. And I've got P matrix. If you remember, P, it is X, Y, Z from the center of our Earth. Then I specify settings for VGS84 ellipsoid to use it in ETF2net function. And here I use each weather as a reference point for particular net reference frame. That's why I put net reference frame at the point of VGS84 ellipsoid and weather location. That's why here I put latitude of radar, longitude of radar, and altitude is 0. It means that our net frame, horizontal plane of net frame, will be put at the ellipsoidal surface VGS84 with a reference point of radar location. I repeat that we use real radars which are located in particular coordinates. That is available in AIP of particular country. Or you can use a variety of different aeronautical databases, civil, which includes all of this data. After this transformation, we've got trajectory of airplane translated to the local Cartesian reference frame of each radar. In this case, x-axis will be directed to the north, y-axis directed to the east, and z directed down, perpendicular down. Next, we need to transform our coordinates of airplane to their polar coordinate system, because radar measures in distance and azimuthal angle. That's why in order to simulate radar operation, we need to simulate errors and put these errors in the polar coordinates of airplane location. That's why I use function Cartesian to polar, and then I've got matrices xnet and ynet with particular airplane trajectory in the reference frame of particular radar to the theta and rho, where theta is azimuthal angle and rho is the distance between radar and airplane at each point of trajectory. Then we've got this theta and rho. It is true airplane location. Okay, in this case we assume that trajectory that we have is true airplane location. Then we need to simulate errors of radars and pack these radars into the airplane trajectory. Thus, first of all, we simulate theta measured. I will add letter M, it means like measured one. And in this case, I will transform from radar to degrees, because after applying Cartesian to polar, theta will be in radians. That's why I will transform everything in degrees, and then I will simulate normal random distribution values with the mean value 0 and standard deviation equal half of degree, and with a particular size to meet the size which we've got in theta matrix. Thus, we can easily simulate measurements by radar in azimuthal scale. However, errors of radar does not connect with azimuthal value. That's why for each azimuth we use half degree error. If we talk about raw measurements, here's absolutely different, because usually standard deviation of raw measurements depends on distance which we measure, and I will use 1% from measured distance. It will be standard deviation for each measured value. In this case, we need to use two loops to cyclically change raw values and to put particular value of random error. Therefore, in this case, I will put that our standard deviation will be equal 1% from measured range. Finally, we obtain theta measured and rho measured. Then we can pack it back to get x net measured and y net measured coordinates of A. Therefore, we apply polar to Cartesian. Then here we need to opposite transformation from degrees to radians, and that's all. However, next we've got measured net systems, and each radar has particular location because all of these three radars are located in different position. That's why we will need to we need to select one radar as a primary radar, and all other radars we will use like secondary radars, secondary types of radars. And then we will transform airplane trajectories from secondary radars scale to the scale of primary radar. Okay, that's why let's use the first radar as a primary radar, and all other radars will be secondary radars. That's why we need to transform airplane trajectories measured from reference frame of second and third radar to the reference frame of first radar. In this case, everything is quite easy. We just need to shift trajectory at particular value delta x and delta y, which is a difference in coordinates between reference point of secondary radar related to the primary radar. That's why we can count delta x and delta y. It will be matrices of 2 for two radars. And then we just add it, and we've got x net in global reference frame. However, our global means reference frame of primary radar. And then we can plot our first picture to see how errors it is. Therefore, airplane trajectory, y-axis and x-axis, looks as following. Thus, radar Kharkiv has the following trajectory. Radar Boryspil, this yellow-orange one, is the following trajectory, and radar in Odessa also the following color. This is x and y, and we will see that trajectory is quite different, and we've got difference like in 150 kilometers. This is because one of these radars, Kharkiv, is located much far away from two other radars. Because Boryspil and Odessa radars are located near the investigated trajectory, and Kharkiv radar locates much far away from our investigated trajectory. Okay, let's go next. That's why we obtain like paths of airplane trajectories into the horizontal plane of net system in reference point of first radar location. Then we use formulas for analytical sigma estimation, because for data fusion we need sigma values. That's why we've got analytical formulas for sigma value calculation based on azimuthal angle and distance to the aircraft. That's why we count sigma x and sigma y for each airplane location and for each radar location. And then we plot it. That's why here we've got sigma values for 3 different radars. And we can see that these sigma values will reach like minimum value at particular location where airplane is close to the radar. That's why sigma, we've got sigma value located reached minimum value because our aircraft here is close to the radar location, and at the blue line here airplane has close location to the Kharkiv radar, and the same to the red one. That's why we've got the following representation of sigma value. Of course, this is ideal situation because range of radar operation is only like between 400 up to 600 kilometers, and we consider much more distance because we applied for the whole airplane trajectory, and you will see that total airplane trajectory like 3000 kilometers, and this is ideal situation because each radar cannot track airplane location in 3000 kilometers range. That's why in real we works only like up to 600 kilometers. That's why in this case we've got huge standard deviation error. Why? Because range quite big, and also we use standard deviation which is multiplied with with the range. That's why we've got this dependence. However, in reality, we work only in this location with a small value, sigma values for closed location to the radar. Okay, that's why it was sigma x, then sigma y, and finally we can apply our formulas x and dispersion for multi-sensor data processing. In this case, we use sum of powered sx by 2 multiply with xnet global. That's why this is formula for fusion of x data, and here it means not measured, it means like multi-sensor. And y multi-sensor means results of fusion for y-axis. And we can find Sx and Sm. And finally, we can plot airplane trajectory that we have. And you will see that the green one in my result, just a second, yep. The green one It is result of multi-sensor data processing. That's why blue one, it is trajectory measured by Kharkiv radar. Red one, trajectory measured by Boryspil radar. Yellow one, trajectory measured by Odessa radar. And the green one is result of data fusion. And we will see that our fusion mostly located at, as a mean value between the most closed trajectories of Boryspil and Odessa radars. And finally, we can count errors because we know true trajectory and we've got results of each sensor measurements, and we've got results of multi-sensor fusion. And we just can count it as an absolute value between from difference between true value and measured values by each radar and by multi-sensor. And finally, we've got the following picture for x coordinate and for y coordinate. And we will see that our multi-sensor also has like mean value between errors. And it will be the same for x and y direction. And probably that's all for my code. That's why multi-sensor data processing with the help of maximum likelihood method or maximum posterior probability give us the best data fusion with the minimum errors. That's why thank you for watching me. I hope this video will be useful for you. Also, I will be glad to share my quotes with you. Thank you very much for watching me. See you again in some other problems solution.